What's up everybody? In today's tutorial we are going to beat the lunar lander environment using double deep Q learning in the Keras framework. You don't need any prior exposure to deep Q learning. We're going to explain everything as you go along. Let's get started. So we have some fairly light imports. We're going to need a dense layer and an activation function. This will be to build our model, of course. We want to import a sequential and load model. That's going to allow us to stack functions, the layers one upon another, and the load model handles loading models from saved files. And of course we're going to want the atom optimizer to handle the gradient descent operation. And as usual you're going to want NumPy to handle NumPy type stuff. So one of the main innovations in deep Q learning is the presence of a replay buffer that allows the agent to sample state, action, reward, new state transitions across many different episodes. The purpose of sampling non-sequential memories is that you are able to get a broad sampling and parameter space so the agent doesn't get stuck in one particular area and have some suboptimal training. So we're going to handle that with a class called a replay buffer. That will just derive from the base object, and the initializer will have a variety of parameters, such as a max size, that's the max number of memories we want to store, an input shape that will dictate, or that will tell us the shape of the observation from the environment. In the case of the lunar lander, it's a vector of 8 elements. The number of actions in the action space, 4 for the lunar lander, in the case of the discrete version. And for completeness, we're going to have a variable called discrete that will default to false. The purpose of this is to allow the replay buffer to work with deep deterministic policy gradients, where you are handling continuous action spaces. So you want to, of course, save your variables. We want a memory counter, which is just the index of the last memory saved. I say index because we're going to be using a set of NumPy arrays to store the state, action, reward, and new state tuples, as well as the done flags. There are many other ways you can do it. You could do something called the DQ, which is a built-in Python data structure. I just like the NumPy arrays because you can pre-allocate everything. Either way is perfectly valid. So we want to start with a state memory, a NumPy array of zeros in shape self.mem size, and good grief, by input shape. So it'll take whatever number of memories you have by the shape of the observation of the environment. And new state memory is going to be basically the same thing. It just captures the new states you get after taking an action. So next up we need an action memory. Action memory, NumPy zeros, self.mem size. By this time it'll be by number of actions, and we want a data type here because the actions will be used to index one of our matrices later, and so it has to be an integer. So it will be let's do this for the sake of extensibility. Let's say dtype equals NumPy in 8 if self.discrete, else float 32. So if you're dealing with continuous actions, the actions aren't actually going to be indices, they're going to be real valued numbers. So that's what we're going to have the float 32 for. If they are discrete, then we want actual 8-bit integers, because it's only going to be 0 to 255. You don't need 64-bit integers for that. That's kind of a waste. So dtype equals dtype, and of course we can go ahead and put that back on the same line. Next we need a way of saving the rewards, and that's just going to be a scalar array of shape mem size, and we're going to use something called the terminal memory. Now the terminal memory is kind of a tricky thing. So the reason we have this is because we are sampling transitions from many different episodes, and even if it were from sequential episodes, it doesn't really matter. But the idea is that when the episode is over, you don't want to sample the next state, and the reason is that the expected future reward for the terminal state is identically 0. Once the game is over, the agent expects no future returns for that particular episode. And so you need a way of accommodating that, and that's through the terminal memory. And that is just going to be an array of numpy zeros and numpy float 32. I think that's for compatibility with some PyTorch code. Otherwise, it could be an integer. PyTorch is a little bit funky. Keras is a little bit more forgiving about data types. Next up, we need a function to store the appropriate transitions in the memory. And that will take state, action, reward, new state, which is called state underscore, and done as inputs. So we want to find the address of the first available memory, and that's just self.mem counter modulus self.mem size. So it will go all the way from 0 up to mem size -1. Once it hits mem size, it wraps all the way back around to 0 again. So that way we overwrite memories starting from the earliest memories. Just a way of keeping the memory finite. You don't want to keep, pending memories ad infinitum. So state memory subindex equals state self.new state. Keep hitting that caps lock button. New state memory index equals state underscore. So if self.discrete, we're going to want to store a one-hot encoding. Actions equals np.zeros. Action memory.shape 1. Actions sub action equals 1.0. Self.action memory sub index equals actions else. Action memory sub index equals action. And of course we want to store the current reward, and we want to take care of the terminal flag. Now you may think it's just done, but in reality it is 1 minus int of done. And the reason is that we are going to be multiplying by this flag, and so when the episode is over we want it to be a 0, whereas when the episode is over the done flag is true, which is a 1, so you want 1 minus the done flag. And also very important, you want to increment your memory counter each time you store a memory. Next up, you need a way of sampling that buffer of memories, and that will take a batch size as input, because you're not going to sample the entirety of the memory to feed through the neural network. You're going to sample some subset, and you want to find out, since you don't want to sample the zeros, you want to sample the memories that have actually been filled. You want to find which is the greater of the which is the lesser of the mem size or the mem counter. Man, having difficulty tonight. So batch is going to be numpy, a random choice, max mem, batch size. So this will give you an array of integers from 0 up to max mem -1 up in the size of batch size. So states equals self.action memory batch. New states self.new state memory sub batch. Actions equals self.action memory sub batch. Rewards and terminal flags. Turn state, states plural, actions, rewards, new states, and terminal. And that is it for the agent's memory. This is, again, just to recap, a pretty significant innovation in deep Q learning, where it allows the agent to sample non-sequential memories. That's where this comes in. We select a batch size from 0, a batch of numbers from 0 to max mem -1. And in general, for a large memory, these will be non-sequential. If some of them are sequential, it's not a huge deal. You just don't want all of them to be sequential, because then you get correlations in your learning that tend to get you caught in one particular corner of parameter space. Next, we need a Keras function to build our deep Q network. We won't need a whole separate class for the deep Q network. I know in some of my other implementations I use a class, but in Keras you don't really need it, so we're going to use a function, and it will take a learning rate, number of actions, input dims, and the number of dimensions for the first and second fully connected layers. So, good grief. So what we want to do is build a sequential model, and this is a Keras construct where you tell Keras you're going to pass in a sequence of layers and you're going to compile that into a module. So it expects a list of inputs, which is precisely what we're going to feed it. The first layer is going to be dense, and that takes FC1 dims as output, and with an input shape of input dims, comma. Now the input dims, comma implies that there is going to be a batch here because we have a comma and then a space, or comma and then an empty element. So that implies we're going to be passing in a batch. This has a consequence for when we choose actions later, and which you will see when we get there. And of course you want to perform an activation on that layer, and we'll use a ReLU for that, of course. The next up is another dense layer that takes input of FC1 dims. It infers it based on the architecture of the network and outputs FC2 dims with another activation and a ReLU, as you may have guessed. And finally, the last layer is going to be an dense layer with an output of number of actions. And so, as I said in the beginning, you don't need to know a whole lot about deep Q learning because I'm going to tell you the gist of it right now. So the gist is that the agent is in some state and says, if I start in this state and follow my policy, the policy just tells the agent how to act. What is the value of each particular action given I'm in some state? And this is the Q value. It's a table, or in this case, a neural network representation of a function that maps states and actions to expected future rewards. The policy is what determines how the agent acts. In this case, we're going to use something called epsilon greedy. Epsilon greedy just means that there's a random factor called epsilon. You roll the dice, and if your dice roll is less than epsilon, you take a random action. If it's greater than, you take a greedy action. So epsilon typically decays over time. So at the beginning of the episodes, you take pretty much entirely random actions, and then over time you start to take more and more greedy actions, and you will settle the epsilon on some finite value such that you still perform exploration, but you take mostly greedy actions. That is deep Q learning in a nutshell. There are many other details, of course, but that's the too long didn't read version. So in Keras, after you build the sequential model, you want to go ahead and compile it, and the optimizer is just going to be atom with the learning rate of learning rate, and the loss function is going to be a mean squared error. And from this function you want to return the model, and that is really it for the deep Q learning portion. This deep neural network will approximate the state value function, the action value function, and it's going to be the heart of the algorithm. So next up, we need to create a class to handle the agent itself. The agent is not just a deep Q network. The agent has a deep Q network. The agent also has a memory. The agent has functionality for choosing actions, storing memories, and learning. So we're going to use, this is a little bit of object-oriented design, but the basic idea is we're going to stick all of that extra functionality in this particular class. And the initialize function takes a whole heap of parameters, a learning rate, we'll call it alpha, a factor gamma. Now the gamma tells you the discount factor for the agent. This means that the agent will reduce the contribution of estimates of rewards from future states to its estimate of the value of a given state. So agent says, I'm in this state, I got some reward, that has all the value of the reward, and then the next state has some value discounted by this factor gamma. And it discounts it because it's taking an epsilon greedy strategy where it may or may not, actually end up in whatever state or whatever set of actions it predicts for the action value function. So we want number of actions, the epsilon, the batch size for our memory, the input dims, a factor that tells us how much to decrement epsilon by, and the minimum value for epsilon, as well as a max mem size. We use 1 million, a file name for saving our file because it's very important, not for the lunar lander environment so much because it executes so quickly on GPU at least, but for other environments. Let's say you want to play Atari games. You'd have to add some more functionality to this. You would need convolutional neural networks to pre-process the images, but you'd still want to be able to save the file in any event. So that will be facilitated by the fname. And finally, for our parameters, we want a replace target. So in Q-learning, the agent, in deep Q-learning, the agent uses two different networks. One network to choose an action, and another network to determine the value of that action. In deep double Q learning, we're going to do something slightly different, but we're still going to have two different networks. You don't train both networks. You only train the target or online network that you choose actions, and then you replace the weights of the target network every 100 games. In this case, that's a hyperparameter of the model. You can do any number. I believe that in the original implementation, the paper by Silver et al., they used 10,000 for the Atari games. I'm using 100 because it's a pretty simple environment, so why not update it more often? The agent has an action space. It's just a list comprehension for I in range self.n actions. Let's go ahead and save n actions. Next, we need the gamma, the epsilon decrement, epsilon minimum, epsilon end. I don't know why I changed from end to minimum. Sometimes I do that, who knows. The batch size, the model file, the replace target, and we are going to need a memory, and that will be a replay buffer of mem size, which in this case is 1 million, input dims and actions, and true for discrete. Q eval is going to be a deep Q network. Takes alpha as a learning rate, and actions, input dims, and we're going to use 256 by 256 as our defaults. We also have a Q target, and that is effectively the same. Here the learning rate doesn't matter because we never actually perform any fitting on that. It's just, the function requires it, so I'm passing it in. Next, we need a function to remember, which just stores the state transitions, state, action, reward, new state, and done flag. So that just stores the memory, state, action, reward. Just an interface function, nothing fancy there. Next, we need a function to choose an action. This is effectively our policy, and this takes a state as input. And this is because the agent is going to choose an action based on its current state. Always important to observe what state you're in, right? It makes sense if you're playing Space Invaders. If you're about to get hit, you want to move out of the way. You don't want to be shooting. So the first thing we have to do is reshape the state. New axis. This will just add an axis to the first dimension, and the reason you want to do that is because up here we have input dims by comma. So this is to allow the network to handle batch training as well as single memory feed forward, which is what we want in the case of choosing an action. It's just a way of preserving compatibility and not having to use two different functions for effectively the same thing. So let's choose a random number from the uniform uniform distribution. If ran is less than self.epsilon, then action equals np random choice self.action space. So if random is less than epsilon, we're going to pick an action at random. Otherwise, you want to calculate the actions predicted by the state, and we did not have to define a predict. That comes from building it out of the sequential and then compiling it. The predict just performs a feed forward of whatever architecture we have defined here. So we will go ahead and feed those forward and then find the most beneficial action. by the argmax. And then we want to return that action. Next, we have the actual heart of the algorithm, the learning function, and this is where things get a little bit tricky, but not too bad. So the first question we have to deal with is, are we going to fill up the agent's memory with random gameplay, or are we going to just start playing and then start learning at some point after we have filled up the batch size of memories? The reason this is important is because if the number of memories saved is less than the batch size, you will end up sampling a single memory batch size times. So in this case, a single memory 64 times. Not really beneficial for training, and that holds true as well for anything up to batch size -1, where you're going to have, effectively the same state sampled over and over again. Not really a good thing. So I always opt for not filling up the agent's memory with random actions, rather just making sure that the mem counter is greater than the batch size. And if it's not, it's just going to go ahead and pass right through the function. So the first thing we want to do is get the state, action, reward, new state, and done flags from our memory. Self, memory, sample, buffer, and we're going to pass in a self.batch size. Give that some more space. Next, we want to go ahead and get out the actual action indices. So basically go back from a one-hot encoding to a regular encoding. Indices equals numpy dot action and action values. You can verify that on a sheet of paper if you want. Next thing you need to do is, actually let me go ahead and switch over to the paper to show you guys what we're going to be doing. Give me 1 second. So here we are in the paper from DeepMind. I believe this is from 2015, a few years old now. What we want to do is, let's take a look here. So this is the update rule for the DeepQ network. And so these are the weights of the network. That's the weight of the new step, weight of the old step. Alpha is our learning rate. YQ is the target we have to calculate. And Q of st a sub t given theta sub t is the state, is the action value function for the state at time t, and action actually taken, the action that we get from the sample buffer at time t. And this quantity y super q sub t is the reward at time t plus 1 plus gamma times the max over actions of the q function of the state at time t plus 1, where you're taking the max over all possible actions. So it's a maximal action given you're in some state s at time t plus 1, or in the parlance of our code, the new states. So in the DeepQ networks, you have a target network down here denoted by this theta sub t dash. That's pretty straightforward. The idea with double Q learning, and I haven't talked about this yet, but the idea with double Q learning is that the agent is using a single network to both select the action and determine the value of that action, and moreover it uses an argmax, so it's automatically overestimating, right, the value of the action value function. So you have this built-in implicit bias of a maximization bias in the algorithm. Double Q learning solves that problem by alternating networks, at least in the non-deep iteration. The deep version is slightly different. I'll show you that in a second. But the basic idea is that you're going to use two different networks, one to find the policy and one to actually calculate the value of the state action value functions. That's the basic idea behind double Q learning. It's just to eliminate maximization bias. For more details, see the free textbook by Sutton and Bardo. They have a whole section on it. It's quite useful, and you can also read this paper. It's pretty useful as well. But the deep version, we're going to replace this particular target function, y super dqn. We're going to replace that with this. And so we still have the reward. We still have the gamma times q, but it's going to be, we're going to stick the argmax inside of the function. So we have to take the argmax over all possible actions for the q function of the new states for the online network, the target, the evaluation network, and we have to feed that action into the queue function for the target network for the next state. So you're going to see that in a second, but it's a totally different way of calculating this target function, target quantity, and the key here is that you're taking a Q value of a Q value of a Q value. Basically, it's a functional kind of functional relationship. So let's see what that looks like in code. So just stick that in the back of your noodle, and I'll show you that presently. So the first thing we need is the value of the next states, target.predict new state, q eval equals self.q eval.predict new state. So that handles the two value functions that we saw. We also want another quantity called q predicted.q eval.predict state. Now this is to handle the y minus q of s and a part. We're going to use this to get the q s of a for the actions we actually took, and this is going to be used for the values of the actions that we calculate to be maximal. So I will show you that. So next thing we want to know are the max actions, and that's just a numpy argmax of q eval for the first axis. Let's set q target equals q predicted, and the reason we do this is because we have to pass in the states to the fit function. So the fit function takes the inputs and the labels, and we're going to use a mean squared error loss. We want to calculate the delta between the target values, which I just showed you from the paper, and the values computed by the Q predicted network. Now you want the differences for the off action columns to be 0. You only want the difference to be maximal for the agent, the action the agent actually took. So if the agent took action 3, then let's say action 2 was the maximal action. You want to take the difference between the predicted values for action 2 and the actual values for action 3. And for actions 0, 1, 0, and 1, you want the delta to be 0. So you have to accommodate that, you have to set q target equal to q predicted, and then we're going to feed that forward through the network in 1 second. Other detail is the batch index equals numpy a range batch size in 32. Now we have to calculate the actual q target values. So batch index action indices. So in other words, the q target will be equal to whatever we feed forward through the evaluation network for the current set of states, except for the actual actions the agent took, and that's going to be equal to reward plus self.gamma times q next batch index max actions as type int. That's just because it comes back as a float, times done. So the done flag is what takes care of the 0 contribution from states following the terminal state. The batch index is just needed for array indexing. That has nothing to do with Q-learning. That's just a Python thing. And the max actions are the maximal actions for the next state according to the Q evaluation network. I hope this is relatively clear. If it's not, leave a comment down below. That's something I can clear up. I actually intend to put all of this in a course later where there will be actual exercises, quizzes, much more exposition. We'll go more in depth on the paper, but for now I want to get it out there and show you guys how it works. So now we have all the parameters we need to do the fitting. We have the states, the Q target, and very important, We want to set verbose to 0, and that's because Keras has the unfortunate side effect of dumping, of word vomit. It'll dump all kinds of stuff to the terminal when you're running it. You don't want it to do that. Set verbose to 0 so it's silent. So what this will do is it will pass forward the states through the network, and that is precisely this quantity here, right? Because these are effectively this, it's this, sorry, it is this quantity right here. And then it will take the difference between whatever it predicts for that and whatever we tell it for this Q target. So by feed forward the states, you get Q predicted, and then you will subtract from that the Q targets. So it's going to take all possible actions and calculate the value of all the possible actions, and for the actions we actually took, it will have the delta. Oh, I have a typo here. That's just next, not next D. It will have the value of whatever the maximal action was according to Q next, which is Q target fed forward with the new states. That's precisely what they implement in the paper. Go ahead and stare at the paper for a little bit and stare at this code, and it'll become clear to you. It's only mysterious in a video. It's actually reasonably straightforward if you think about it and read the paper at the same time. Next, we have to handle the epsilon decrement. So that's self.epsilon times self.epsilon decrement if epsilon is greater than self.epsilon min, else it's self.epsilon minimum. And finally, if self.memory.mem counter modulus self.replace target is 0, then it's time to update network network parameters. So let's go ahead and define that function of update network parameters. No inputs needed for that. Self.qTarget.model set weights. Self.qEval model get weights. So this will just get the weights from the evaluation network and copy them to the target network. Two other functions. We want to save the model and say self.q eval save self.model file. We also want a function to load the model, and self.q eval equals load model self.model file, and this function can only be called after you've instantiated the agent. And so we will have, after calling this function, we will have a target network with random parameters and an evaluation network with optimal parameters, which we don't quite want. So if we are in evaluation mode, meaning equals epsilon min, then you want to update network parameters. I'll say less than or equal to, because I like to pass in 0. So less than or equal to epsilon min, update network parameters. And that's a function, not an object. So that is it for the Keras code. Let's head over to the main file and start writing code to test all of this out. So we want to import gym. Let's comment this out from gym import wrappers, and that is just for the wrapper to actually display the output of the gameplay to the screen. It's how I generated the videos for the beginning of this particular tutorial. I need NumPy. From our model, let's import the DDQN agent and plot learning. I didn't do a learning plot for this because I screwed it up, and then it takes a long time to run, so whatever. We'll make do without it. I'll show you the output to the terminal for a couple different games so you can see that it learns under at least a couple different sets of conditions. First thing you want to do is make your environment, and that's lunar lander v2. Next you want to create your agent and an alpha of 0005, gamma 99, 4 actions, epsilon starts out as 1, batch size 64, and 8 input dims. Nothing mysterious there. We're going to play 500 games. If you were loading a saved model, you would do that here. Agent.load model. In any event, you're going to need a list to keep track of scores, a list to keep track of your epsilons. That's so you can see how this score evolves as a function of decreasing epsilon. It turns out with this epsilon decrement, the epsilon goes to 0 really, really quickly after just a few games. So it's a very steep line, and then it's 0, so or 0.01 rather. So there isn't a whole lot of time spent with random actions. If you want to do the saving of the output, you would do that here. Wrappers.monitor env temp lunar lander video callable equals lambda episode ID true, force equals true. This will just record for every episode, and it will overwrite anything in the folder. So make sure you use different directories if you are testing out different models. I've made that mistake before. Quite a silly mistake. Don't be me. Next, let's actually start playing our games. For I in range end games, set the done flag to false, set the score for the episode to 0, and reset the environment. While not done, you want to take the choose the action given the current observation. You want to get the new observation, the reward info, done, and info from the environment by stepping the action. Let's keep track of our score and remember these sets of transitions: observation, action, reward, observation underscore, and done. I believe I have int done in the class, so that doesn't need to be done here. Observation equals observation underscore. You need this line so that way when you come back to the top of the loop, you're selecting an action based on the actual new state, not the old state. Agent.learn, and at the end of every step you want to learn. If it wasn't clear to you, if you're unfamiliar, Q-learning is a type of temporal difference learning, meaning that it learns at each time step of the episode. So it's also well suited for continuous tasks as well as episodic tasks. At end of the episode, let's go ahead and append the agent's epsilon value and qn scores dot append score. Let's calculate an average score. The reason you want to do this is so that you can kind of get an idea if the agent is learning. qn scores max 0 I minus 100 up to I plus 1. That'll just take the average of the last 100 games or the whatever if it's less than 100 games. Print episode I score %.2f modulus score average score 2f average score. And if I modulus good grief modulus 10 equals 0, then we want to save the model, and I greater than 0, ddqn agent save model. Finally, at the end of the games, let's say file name equals lunar lander ddqn.png. We'll need an x for the plot learning function. I plus 1 for I in range and games, and plot learning x scores eps history file name. And you can find this plot learning function on my GitHub. It's just in the utils file. It's just a simple file function to plot the learning plot for the agent. So I've saved that. Let's head to the terminal and see how many typos I made. All right, and here we are. Main Keras DDQN. Invalid syntax, line 103 in DDQN Keras. Oh, I see it. I forgot the backslash. Let me show you. So line, what is that, 103? It's right here. Got the slash. No big deal. Let's go back to the terminal. Let's try it again. Cannot import name DDQN agent. Did I misspell it? So it is in fact DDQN Keras. So if I look here, DDQN action. Agent. There we go. That'll do it. All right, let's go back to the terminal. Another thing is that I just updated my TensorFlow to 1.14, trying to get some TensorFlow agent stuff to work, and I get all of these stupid warnings here. I don't know what that's about, but whatever. Name input shape is not defined. Oh, it's because there is missing an equal sign. Let's take a look. That is on line 45. Input shape equals. That's a silly mistake. Back to the terminal. Compile missing one required positional parameter optimizer. I misspelled optimizer. I forgot the I. 1 second. It is right here. I forgot the I. Optimizer. That doesn't work. Once again. Expected dense one input to have shape 8, but got array with shape 4. So that seems like it's passing in like something with size and actions. That is in the QEval predict state. Let's take a look. So it says expected dense one input to have shape 8, but got array with shape 4. So that seems like it's passing in an action. Let me see the sample buffer. Go states, action, rewards, new states, terminal. Let's go back down here. State, action, reward, new state, done. State, action, reward, new state, done. That's right. New state, state. Which line? 95. Q eval predict state. So then I wonder if state, action, reward, that's saving. Did I change the shape here? State memory is input shape. Storing that. Ah, right here. Self.state memory. Perfect. That's easy. All right, let's go back to the terminal. DDQN agent has an attribute batch. That's because it's batch dash size instead of batch minus. Line 101. So let's come down to 101. I hate that. All right, terminal time. Once more. Ooh, another typo. A DT type. All right, I'm just going to delete that instead of switching the windows. That is line 101. D type. All right, let's try it again. Name action indices. Okay, you know what? Let's do this. That's down here. That's easier than switching windows. I hope you guys don't mind. I'm using Nano. I should really learn to use Vim, but Nano is so straightforward. Update network parameters. Oh, that's because... Oh, okay, let me go back to the code editor. I'll show you why. So basically, all three of these functions are within the scope of the learn function. Let's tab those back. Now they are just within the scope of the class. That should be good. 1 second. Let's try it again. Yes. All right, so it's running. So I've run this a few times before and haven't managed to get a learning plot. Once because I didn't try, another because I put the epsilon history in the wrong place. So let's take a look here. You can see ran 499 games, ended up with a final score around 244. That's considered solved by any definition. This is an average over the last 100 games. And it took a little while to actually figure out how to play. You can see going all the way back to the beginning that it had, pretty reasonable average scores, minus 100 or so. So that's not too hateful. And you can even see, I believe, now this one is pretty much straight up. So let's take a look at another example. Here's where I screwed up the plotting, but you can see that it didn't quite solve it. This is with a different replace target iteration. This is with 100, and the other one is with, I think, 250 or maybe even something larger. I can't remember. But you can see it still gets some low scores, and I suspect that's due to the, in part, the epsilon min. So, but it still learns. It gets over 200. It does technically beat the environment by the standard definition. It's just that it eventually kind of decays off, and it would come back up if you let it play a little bit more. If you read the original paper, when they show the plots, they have kind of like error bars, not really error bars, but there is a spread of rewards, and they plot the median as well. So because it's a probabilistic kind of thing, and where we start in parameter space is probabilistic as well as the action selection. So there's going to be some variation run to run, but it is solved by the standard definition of the word. So I call that a W, call it a win. I hope this was helpful for you. Any questions, comments, leave down below. I will link a companion article that talks about deep Q learning on my website, so you can get a little bit more background information if you're new to the topic. Make sure to subscribe if you've made it this far, and I look forward to seeing you in the next video.